Okay. Thank you all for coming today. My name is Wendy Rocho, and I am the Assistant Director for the College of Technology and National Center for Next Generation Manufacturing. I'll be substituting for Dr. Karen Wosczyna-Birch, our Executive Director and Principal Investigator today. And I'm just going to provide a quick overview of what we do. Thank you again for attending. This specific webinar in this series is on careers and trends in lasers in manufacturing. I saw a sneak preview of some of the videos in this yesterday, and it's just fascinating what can be done in the precision that is involved. So next slide, please. Thank you. So the College of Technology is the umbrella over the engineering and technology programs in the Connecticut State Colleges and University system. We are 12 community colleges and 10 public and private partner universities. We oversee the curriculum in engineering and technology, including advanced manufacturing, and make sure that those programs, the associate's degrees, transfer onto our university partners seamlessly. We also have industry-driven curriculum under the COT for micro-credentials and certificates, as well as the AS degrees and high school partnerships that allow students to join the workforce as technicians upon completion of the programs, or again, they can transfer on for that bachelor's degree, or they can join the workforce and come back. We make sure that there's multiple entry and exit points that are very responsive to industry needs. A sample of some of the programs that we have regarding advanced manufacturing are mechatronics, machine technology, welding, electronics, and electromechanical maintenance. Yep, next slide, thanks. So our National Science Foundation funding began back in 2004 with funding for the Regional Center for Next Generation Manufacturing. That is under the Advanced Technological Education Program, which focuses on technician education through community colleges. In addition to that 2004 funding, an additional 2 rounds were funded for expansion of the regional center. And then eventually we received funding to transition to a resource center. So the regional center has been sunsetted, but last year we received $7.5 million from the same program to establish the National Center for Next Generation. This focuses on Industry 4.0 as applied to, you'll see it in the next slide, different disciplines in manufacturing. And our goals are to develop a national manufacturing leadership network to help advance workforce development within the advanced manufacturing discipline. We also want to create a repository of advanced manufacturing education resources, provide faculty and instructor professional development, as well as counselor development to really make sure everyone is aware of the lucrative and successful careers that are out there in advanced manufacturing, and also to just improve the image of advanced manufacturing in general. We are national, so we had to bring in some national leadership on this. Our 4 main partners on the leadership team are College of the Canyons in California, Columbus State Community College in Ohio, Central Community College in Nebraska, and Indian River State College in Florida, who is our partner on today's webinar. We also partner with the manufacturing extension partnerships. Each state has one of those. Diversity consultants and consultants with numerous expertise in other areas too. The Manufacturing USA Institutes and obviously other national centers and projects under the NSF ATE program, including industry and the business and industry leadership team model. Next slide, please.
Oops.
Oh, that's okay. That's okay. I know what it says. So Industry 4.0 is the focus of the National Center, and under that, manufacturing is just so broad. So we had to come up with a way of how to divide it into sections. So we have a design team, a fabrication team, a processing team, quality control and supply chain, and then a team for industry 4.0 as well. And what that does is divides out the technologies and gives us a way to have a little bit of control over them. And the teams meet to see how industry 4.0 or now even industry 5.0 can be applied to programs that already exist in advanced manufacturing across the country. So our goal is to just build that workforce, make sure everybody is learning the technical skills that they need to know and the professional skills that they need to know to be successful in the advanced manufacturing workforce. And next slide. And with that, I'd like to introduce Dr. Chrys Panayiotou from Laser Tech, which is also a National Science Foundation Center. And that one is out of Indian River State College in Florida. So with that, I'll pass it over to you. Thank you.
Thank you, Wendy. And hello, everybody. I'm very glad to be able to present to you a little bit about lasers and applications of lasers in manufacturing today. I'm the principal investigator of Laser Tech, which is a National Science Foundation Center. We're located down in Fort Pierce, Florida, but we have another 44 colleges throughout the country. I'm also a co-PI on this very important project or center, the Next Generation Center for Manufacturing, which Wendy and Karen are leading. And with that, let's get into our presentation. So here's an outline of what I would like to present today. We'll start with a short introduction to the laser. We'll have laser applications in general. Then we'll dive into specific applications of lasers in manufacturing. Then we will talk about jobs for technicians and the market outlook. And then we'll finish with the Laser Tech resources for educators, which we have available for you. The laser is relatively new technology. The first laser was invented and demonstrated in 1960, and this industry and this specific piece of equipment didn't mature until the 2000s. By the 2000s, the cost of lasers have been dramatically reduced, making them economically feasible in all sectors of the economy. In manufacturing specifically, which we will talk more about today, lasers are used for cutting, marking, welding, drilling, surface cleaning, surface treatment, additive manufacturing, micromachining, disinfecting medical devices, and tweezers manipulating nanoparticles. Laser power can range from a heavy amount of power, tremendous amounts of power, which allow the melting of missiles in the sky far away from a laser, to very, very much more delicate lasers, which can drill 50 nanometer hole diameters in microchips. Lasers used along with robotic automation increased productivity and reduced costs dramatically in the last 40, 50 years. Because there's a shortage in laser technicians, companies offer salaries well above the national average for technicians. So let's, like I said, this is a short introduction to lasers and why lasers are able to do what they do. What's really different in lasers than any older type of technologies? Well, laser light is unique. It is man-made and has the following two key characteristics which make it different than all the other types of man-made light or natural light. The first one is monochromaticity. A laser light has only one color. We also have lasers which have colors which we don't see. So the better way to refer to lasers is by the wavelength of that radiation. So being monochromatic allows laser light to be selectively absorbed, transmitted, or reflected by different substances. So monochromaticity is one key parameter. The second key parameter of the laser is coherency. It's coherent light, which enables you to have high energy density. Coherent light means that all of the rays emitted from the light source, they are all in unison. They are all have the same phase and frequency, and they are emitted in the same direction, which creates this high energy density. So let's look at some examples of these two properties. Let's begin with the monochromaticity. So if you look at the picture on the right, is a laser beam which has a wavelength of 1064 nanometers, which is in the infrared light. It's not visible, and has the property of transmitting through human tissue without damaging the tissue, and it's able to ablate and destroy a cancerous growth, which absorbs all of the energy, and it can be up to 10 centimeters deep below the skin surface. Another application is of a different type of a laser at 415 nanometers, which is ultraviolet. And most of the UV light cannot easily be penetrated and absorbed through the human tissue. But what it does, it burns, or it is absorbed by the top surface of the human tissue, of the skin, which makes it suitable for treating skin conditions such as acne, eczema, and psoriasis. So you can see in these two examples, two different wavelengths, two different colors of light, which have two completely different effects. The last example here on this slide is a laser light of 10,500 nanometer wavelength. It is produced by a CO2 laser, carbon dioxide. And at this wavelength, iron is the type of material that can absorb most of this energy and allow us to cut iron. But as you can see here, we cannot cut aluminum at that wavelength because of the different characteristics and absorption properties of aluminum. So after experimentation, they figured out the 900 nanometer is the light that can best cut aluminum. So with this slide, you can see that this property of single wavelength or very narrow band of wavelengths, along with the properties of the material of absorption and reflection, create all of these applications of lasers. Now let's talk a little bit about coherency, or the high density of lasers. Here, the first example shows a 100-watt laser. If you think about a 100-watt light bulb, which is very common in our homes, this is a laser with about the same amount of power, 1,100 watts. But with focusing optics, we can concentrate all of that energy onto a single spot. And the energy density at that spot, it will be 100,000 watts in that little tiny geometry, which is sufficient to melt the metal. And in this case, it's melting the outer skin of a drone and eventually bringing it down. The same application is used in this picture on the right, where the high intensity of the laser beam is used to make these holes or cut holes on a metal surface. Now, we humans using these lasers, we have to be careful, because that high intensity and high energy can be dangerous if we don't control it properly. So here's an example of a 1 milliwatt laser, which is a laser coming out of a laser pointer, for example. And if it focused properly into this 1,000th of a millimeter square spot, then the energy density at that spot will be equivalent to 1 watt. And 1 watt is enough to cause eye damage. So looking at this picture on the right, all of that energy would go through the lens of the human eye and will be focused on the retina, which will cause permanent eye damage. So we have to be careful and be aware of these issues with lasers. The applications and the application market is huge. You can find lasers today everywhere. You can find them in medicine and healthcare. And I will not read through all of these applications. You will have the slides later on if you wish, and you could go through them. You will find lasers in consumer and entertainment industry, in defense and security, in scientific research, and of course, manufacturing, which is the purpose of this webinar today. And we will go through all of these different applications in manufacturing in the following slides. So let's begin with metal cutting. As I said earlier, depending on the metal we want to cut, we choose the right laser with the right wavelength, which will allow the maximum absorption of the energy and cut the metal easily. So we can cut metals as thick as 1 inch with this type of a laser, the appropriate type of laser. Here's another example of doing more delicate work by cutting a stent. This stent was cut with a laser, very, very fine work. And you will see a video pretty shortly showing a stent cutting scenario. But let's begin with the first video that shows cutting of metal. It's a metal piece, it's a part of a car. And you can see how easily this laser cuts the metal. It's mounted on a robotic arm, and under the control of the robotic arm, you have especially this type of robot with 6 degrees of freedom. It can cut at any angle, rotate it, and do it so quickly and effortlessly that a human, it's impossible for a human to do. So let's watch it. So you can see how it bends and cuts at all angles, and the cut is nice and clean. And after the piece is cut, the post-processing is basically minimal. You don't need to do anything else for that part to be used. So here's another video, which is the stent. And of course, this is a close-up. These stents are much smaller in size. And let's watch the video with the laser up here on the top cutting. Notice most of these laser beams, if you don't see the beam coming out, are in the infrared region, above 700 nanometers, which we cannot see with the naked eye. We can only see at the point where the laser melts the metal. You see the sparks flying and the light being diffused. So here is how it cuts nicely and cleanly the pieces of the tube. And at the end, you have a medical stent produced by this laser. On this slide, you can see an application in drilling. It can drill metals, ceramics, and plastics. This is a big industrial drum, and all of these tiny holes that you see, they have been drilled with a very powerful laser. To the contrary, on the right, we have these holes which have been drilled with a very different type of a laser, and because these holes are way, way smaller in geometry. As you can see down here, This is 100 micrometers. That's the this length of this line, and these holes are about 50 micrometers in diameter. So different lasers for different applications. This video will show metal drilling. So when I started, pay attention to how the holes are cleanly cut, no debris left, and then everything falls on the bottom, and it's cleaned with vacuum. And at the end, you have a final product which doesn't need much post-processing. Marking and engraving is another application of lasers. And we can mark on metal, plastic, ceramic, leather, any kind of material we can mark. And in those cases, you have to match the wavelength of the light with the material, the absorption of the material on which you would like to mark. And everything is done under computer control. So you have any kind of an image you may have. It can be a barcode, it can be a more complicated image. Once you can create it on the computer, then you can have that image marked or engraved in any type of material using the right wavelength. So here's another example. It's a short video that shows laser marking on metal. So when I started, pay attention again to the laser, how quickly it removes the top layer of this material, and under computer control, the laser marks the image that was provided by the computer which had the image. So very quick and very precise, and we couldn't do these things years ago without lasers. The ability to mark and engrave in years before the laser were very, very limited. Another application is welding and brazing. Here on the left, we have an automotive assembly line. Here is a car, and on the four corners, front and back, there are four robotic arms, which are tooled with lasers at the end. And then those four lasers together under the control of the same program, they're able to weld, as you can see in the middle picture here, where the red lines are. That's where the welds are being done by those four lasers. And typically, in this specific car, there were 3,000 welds that were done by these four lasers in a time frame of 1 minute. That's amazing. Another application is the pacemaker that you see here on the right, where, as you understand, you need to have precision and you need to have results that there will be without any flaw, because this will go into someone's body and you don't want to have to go back and repair it or take it out and fix a problem that happened during the manufacturing process. So precision welding for pacemakers is another application. We have a short video that demonstrates the welding of those 3,000 spot welds in the automotive industry. Look here on this assembly line, you have several cars. In this specific assembly line, they can handle up to 50 vehicles at a time. And for each vehicle, there are four robotic arms with lasers are attached to them, performing those welds simultaneously. So let's take a look at the video. So again, all of these things are available and enabled by lasers and automation. And in decade ago or earlier, all of these things were impossible. Another application of lasers is in cladding. And cladding is basically metal deposition on another metal structure to make it harder so it can increase the lifespan, or to repair damaged metal surfaces. And examples are in mining industry and aerospace industry. This picture here on the right shows cladding, laser cladding of a high pressure valve, so it can last much longer. And here is laser cladding of a steam of the blades or a turbine's steam, turbine engine, where the superheated steam hits the blades and really starts pitting and damaging those blades. So cladding it with laser extends the lifetime of those blades. It can also be used to repair blades which have been pitted over the extended use. 3D laser metal 3D printing or laser additive manufacturing is one of the newest applications of lasers. Here on the left, you can see a nozzle which shoots down 3 streams of metal, powdered metal. So what you see here, these gray lines are the powdered metal. The laser beam comes out of the middle and is not visible, it's infrared. But at the point where the 3 metal powder streams meet, that's where the laser is focused. It melts the metal and deposits it on this basis material. So on the right, you can see a finished product. This is one of the very early pieces which made laser additive manufacturing very known and desirable to industry. This is a nozzle which is used in GE engines. And before making it with laser additive manufacturing, it used to be made with 18 different pieces assembled together. So now it's just one piece, and it has much higher reliability. So some of the pros and cons of laser additive manufacturing. The pros, they can make extremely complex parts. The parts are strong because they're made with these new alloys that we have today. Lightweight, creates little waste as opposed to the old type of manufacturing, which wasn't the additive, it was the subtractive manufacturing, a lot of waste. High reliability and repeatability of parts, and on-demand production. All of these are pros. Cons, slow building time. For example, that jet nozzle that you've seen, it took the original one about 20 hours to be made. To make it more time efficient, they make several of these at a time in one production run. Another negative is the limited number of metal powders. These metal powders, they have a limited shelf time, and they're made of these special alloys. They have these formulas which are made to easily melt with the wavelength that we talked about earlier, and different types of wavelengths. The finishing surface is not smooth, so it needs some post-processing. That's a negative. Size of part is limited by size of the machine. So if you want to make a huge part, you have to have a huge machine, and these machines are expensive. To give you an idea of the cost of these machines, one of the lower cost LAM machines is about $500,000, and small volume of production. So because of these pros and cons, you have to select an application of laser additive manufacturing where the pros are more important to you. Another application of lasers is hardening of metal using heat treatment. So I will start the video here. You can see you will see the laser being shining here and hardening this gear to prolong its life or extend its lifetime. This is used in places where you need to have metals which you need to extend their lifetime. For example, tools in some expensive household items. That's a very common use of laser hardening. Let's talk about jobs for technicians and the market outlook. We have about 420 openings on average for technicians every month. The average entry-level salary is about $65,000 a year, with 5,000 to 10,000 sign-in bonuses. This is feedback we have from students who are finishing our programs and getting jobs. And these jobs are available in all 50 states with higher concentration in more industrial areas. To find more about where these jobs are and which companies are hiring and in which specific cities, if you go on our website where we have an archive of our newsletters, you will see on our newsletter on the left-hand side, we have all of this information about all of these jobs which are available, and you can go back as far as 2 years back. Other resources we have available for educators. We have 5 courses which are hybrid. You can do the theoretical part of the course online, and then the practical part of the course with labs can be done at our labs at Indian River State College in Fort Pierce, Florida. So we have introduction to photonics, geometrical and physical optics, fundamentals of fibers and fiber optics, laser systems and applications, and introduction to spectroscopy, which is under development right now. We also have open education resources in the forms of textbooks and other printed material. Here is a sample of what we have available, and you can go on our website and download this at no cost. This one here showing the $100 cost, this is from a few years back that we used to sell it. Now we have it available for free download. We also have available lab kits and experiment manuals. These are inexpensive way to start teaching some of these courses. And we have 3 different kits and experiment manuals here. And we also have available instructor materials, like test banks and PowerPoints and videos and things of this nature. In addition to all of these resources, we have more. This is a screenshot of our website. We have posters available, we have outreach materials, external collections, and career preparedness resources. So you can visit our website and look at all of those other resources. We are located down here in Florida on the Atlantic beach coast, Atlantic ocean side. And here's my email and my phone number and our website. Feel free to contact me in any way that you like, and we'll be more than glad to help you in any way we can to incorporate laser photonics in your courses or programs. And with this, thank you very much, and I will pass the microphone to Wendy.
Thank you, Chrys. Oh, there's the 3rd slide. We actually do have one question. So before I wrap up, let me do that.
Okay.
I don't know if you can see it too, but I'll read it to start. I don't understand the units there. And Jacob can let you know what slide if you need to go back. But my understanding is the power of the 100-watt laser is still 100 watts, as conservation of energy doesn't allow for creating power out of nowhere. The light intensity is power over area, so by using focusing optics, you can make the same power have a much higher intensity. The units of intensity there would be power per area. Am I correct? Or if not, please explain, or watts over meter squared.
Okay, yeah. Everything that he said is correct. We're not creating power out of nowhere. We're just focusing the same amount of energy in a smaller area. So if you have 100 watts focused on a circle of, let's say, 1 inch diameter, and then you take all of that energy and you focus it on 1 millimeter diameter, then you're going to have a higher intensity. It's just reducing the area which receives the energy.
Thanks. Yeah. So it was just that slide that was showing like 100 watts going to like 100,000 watts or whatever. So
yeah. So we actually reduce the energy, the area, by that amount that seems to have amplified. That's how you get it. That's how you are able to drill a hole, a tiny hole, with that amount of energy that you originally had in your laser. You have to focus it.
We have another question. Is there a role for semiconductor lasers in manufacturing?
Is there a role
for semiconductor lasers in manufacturing?
Is there a role or a room? I didn't quite get the question.
Probably a role, I'm guessing, Wendy?
Yep, role.
Role in there?
Richard,
Yeah, a role.
Feel free, ROLE.
Oh, okay. Well, depending where you want to drill a hole in semiconductor or a semiconductor substrate, then you're going to use the different type of a laser wavelength, and then the power of the laser depends how thick is the substrate or how deep is the hole that you want to drill. And usually for those types of substrates, we're using UV or excimer lasers, which have a lower wavelength, which is higher frequency and higher energy.
Okay, any other questions? Oops. Okay, next slide.
Oops. Yeah, that's it.
Okay, and then just so you know, this is our second to last in this educator series of webinars. So our next one is going to be on May 20th, same time, 1 p.m. Eastern, and that's going to be on Industry 4.0 specifically. We're going to have a panel of educators, representatives from other NSF ATE centers and projects and industry to talk about applying that to your advanced manufacturing programs. And if there's no other questions, we'll adjourn this webinar, and please feel free to go back to the recording. It will be available on our website as well as all of our previous webinars on supply chain, mechatronics, and welding. Thank you for attending.
Thanks, everybody.